Your modern engine is a ticking time bomb, and the oil you're using is the fuse. While Europe demands high shear protection, American standards are sacrificing your car's longevity for a tiny boost in fuel economy. We are uncovering how thin, low-viscosity oils are literally disintegrating under heat and turning your engine into scrap. Let that sit for a second.
103. 103 out. Yeah, they got him a white baseball cap on. Not at the time, but they said they both say mid-20s.
Because I know how that sounds. It sounds like the kind of thing someone says to get your attention and then walks it back. I'm not walking it back. What I found when I actually went through the specifications, the real documents, not the summaries, is that the gap between what American oil standards require and what European engineers actually designed your engine to run on is not a minor technical footnote. It is a real difference with real consequences, and most car owners have no idea it exists. Think about what's happening inside your engine right now. Metal surfaces moving past each other at thousands of revolutions per minute. The only thing standing between those surfaces and direct contact is a film of oil. Not a thick cushion, a film, microscopic in places. And that film has to survive temperatures above 150 degrees Celsius, pressure from combustion, and the constant shearing force of metal moving against metal. If that film fails, even partially, even for brief moments, you get contact, wear, damage that accumulates quietly for years before it announces itself as a repair bill you were not expecting. What are you driving right now? And more importantly, do you actually know what oil specification your engine was designed for? Not what the sticker on your oil cap says, what the engineers who build your engine actually specified. Most people don't. I didn't for a long time. Tell me in the comments, because the answers I get on videos like this genuinely shape what I research next. And if you want to keep getting this kind of information, the kind that takes actual time to dig up, subscribe now. There's more like this coming. Now, where does this divide actually come from? Because here's what I want you to understand. This is not a conspiracy. The people who made these decisions were not trying to destroy your engine. They were optimizing for something real. They just didn't put the trade-off on the label. The API, the American Petroleum Institute, has been setting oil standards in the United States for decades. And those standards evolved in a specific context. American cars, American driving patterns, long highway stretches, relatively low revving engines, and an industry culture that assumed frequent oil changes as the baseline maintenance behavior. API standards are legitimate, they are not fake, but they were built around American priorities. And then there's CAFE, the Corporate Average Fuel Economy Regulations. If you want to understand why American oil went in a specific direction, this is the moment. CAFE regulations penalize automakers whose fleets don't meet federal fuel economy targets, and one of the ways automakers found to squeeze out marginal improvements in fuel economy numbers was thinner oil. Thinner oil creates less internal friction. Less friction means marginally better efficiency. Marginally better efficiency means better CAFE numbers. Better CAFE numbers mean avoiding federal penalties. That is the moment where American and European standards actually split. Not because of engine science, because of one regulation that had nothing to do with engine protection. The improvement from switching to thinner oil is real. Going from a 5W30 to a 0W20 might buy you 0.5% to 1% better fuel economy. Real, measurable, worth something in aggregate across millions of vehicles. But that gain came with a cost, and the cost was paid in a currency most owners don't know exists. Meanwhile, across the Atlantic, ACEA, the European Automobile Manufacturers Association, was developing standards built around different problems. European engines were smaller displacement, higher revving, under more thermal stress. European driving included extended autobahn runs at sustained high speed. European manufacturers were also pushing longer service intervals, not shorter, and European regulators were dealing with emissions through hardware improvements on the engine side rather than just fuel formulation. The priorities were different, the engineering requirements were different, the standards ended up different. Stay with me, because the specific number that tells you whether your oil is actually protecting your engine, most people have never heard of it. It's called HTHS viscosity. And once you understand what it measures, you will not be able to look at a bottle of motor oil the same way again. HTHS stands for high temperature, high shear, and the name tells you exactly what it measures, the behavior of oil under the conditions that matter most. Not cold startup, not moderate highway cruising, the extreme end, 150 degrees Celsius, with oil being squeezed between two metal surfaces moving past each other at a shear rate of 10 to the 6th reciprocal seconds. That's the number. That's the condition that approximates what happens in your engine bearings at highway speed with the engine fully warmed up and working hard. Here's how to think about it. Imagine spreading honey across a metal surface. Cold honey is thick and slow. Warm honey flows faster, spreads thinner. In most contexts, the warm honey behavior sounds ideal. It gets everywhere. It flows into gaps. But imagine those gaps are between two metal parts spinning past each other at high speed. The honey needs to stay thick enough to keep those parts from actually touching. If it's too thin, if it flows out from between the surfaces before it can maintain a protective film, the surfaces touch. Just briefly, just microscopically. But that contact is wear, and wear is damage. And enough of it, accumulated over 60,000, 80,000, 100,000 miles, is an engine that fails before it should. Now here's where it gets specific. A new engine, designed around 0W20 oil, like many modern American market engines, is machined with tighter clearances to compensate for the thinner oil film. The engineers accounted for it. They designed around it. The thin oil is appropriate for that engine because the engine was built to run on it. But what about a high-revving, turbocharged German engine, a BMW inline-six, a Volkswagen 2-liter TSI, or a Mercedes-AMG 4-cylinder, engineered to European specifications, sold in America through an American dealer, with an oil cap that says, "Use API certified oil"? That engine was designed to run on oil meeting BMW LL01, or VW 50200, or Mercedes 229.5. The American standard is technically complied with. The engineering specification the engine was actually built around is not. And nobody in that transaction told the owner. Nobody will until something breaks. The specific engines most vulnerable to this, I'll name them because this matters, are any turbocharged engine with variable valve timing, any European origin engine sold in America without a clear OEM specification in the owner's manual, and older engines with looser machining tolerances that assumed higher HTHS values from the factory. These are not obscure vehicles. We are talking about millions of cars on American roads right now. The math made sense on paper. The people who made this decision were not incompetent. They just optimized for one thing and accepted that something else would get worse. The thing that got worse is your engine's long-term protection, and nobody put that on the label. The first time I actually read an ACEA specification sheet, and I mean read it, not skimmed a summary, I had to go back and check if I was interpreting it correctly. Because the gap between what the European standard requires and what you're likely running in an American-bought European car is not ambiguous. It's right there in the numbers.
Let me tell you what BMW's Long Life 01 specification actually requires. LL01 is BMW's internal engineering standard, not a suggestion, an engineering requirement, written by the people who designed the engine and know exactly what it needs to survive. It requires oils to maintain viscosity stability through extended drain intervals of up to 30,000 kilometers. It requires specific shear stability performance. It requires specific oxidation resistance. The typical ATI SP oil sold at American auto parts stores meets none of those requirements. Not because the oil is bad, because it was never designed to meet them. It was designed to meet different requirements. VW 502.00 and its siblings 504.00 and 507.00. These are Volkswagen's specification approvals. If your VW or Audi requires a 502.00 oil, that approval is not interchangeable with an API SP rating. The 504.00 and 507.00 specs are specifically designed for extended drain intervals in direct injection engines with DPF systems. Using an oil without those approvals and then following an extended drain schedule is the exact scenario where oil degrades past its effective protection window while the owner believes they are maintaining the car correctly. Mercedes-Benz has 229.3, 229.5, and 229.51, different specifications for different engine families, with 229.5 requiring a minimum HTTHS of 3.5 and a full synthetic base. Using the wrong Mercedes spec is not a minor substitution. The engine was engineered around a specific oil behavior. Substitute a different spec and you change the behavior. The timing chain failure pattern is the one that made me actually angry when I dug into it. Give me 2 minutes on this. Timing chains are not supposed to be a maintenance item. They are supposed to last the life of the engine. On many modern turbocharged engines, certain BMW N47 diesels, early Volkswagen TSI engines, some Range Rover Sport variants, timing chain wear and failure was occurring at 60,000, 80,000 miles. Not 200,000, not at the end of a long life, at 80,000 miles on cars that were maintained by their owners, by people who changed the oil, who followed the service schedule, who did what they were told. I've talked to owners who had timing chain issues at 80,000 miles on cars that were maintained properly by every standard they were told to follow. They just weren't told which standard actually applied to their engine. A timing chain replacement on many of these engines runs $2,000 to $4,000. And the relationship between oil specification compliance and timing chain wear, it's not theoretical. The chains are lubricated by engine oil. Their tensioners are hydraulically operated by engine oil pressure and viscosity. If the oil's film strength is insufficient, wear accumulates on the chain guides and tensioners in ways that don't show up at 30,000 miles. They show up at 80,000, at 100,000, when you think you've done everything right.
The turbocharger is even more direct. A turbo bearing spins at up to 200,000 RPM in some applications. The clearances are extremely tight. The lubrication is entirely dependent on engine oil arriving under pressure with sufficient viscosity to maintain a film across those bearings. If that oil has sheared down under high temperature operation, if its HTHS viscosity has fallen below the protective threshold, bearing wear accelerates sharply. Turbo replacement on a modern turbocharged engine typically runs between $1,500 and $3,500, depending on the application. And then there's sludge. Oil that breaks down faster than its rated interval because its shear stability was not sufficient for the operating conditions, produces degradation byproducts that accumulate in oil passages and galleries. Once sludge forms in narrow oil galleries, oil flow to critical components is restricted. The damage from restricted flow is cumulative. In severe cases, it can total an engine, worth $8,000 to $15,000 to replace. Has your car had an expensive repair, timing chain, turbo, something major that happened earlier than it should have? Drop it in the comments. I'm genuinely curious how widespread this pattern is, because the data I've seen suggests it's not rare. If you've been finding this useful, and I think you have because this does not get talked about in any of the normal places, subscribe. We do this kind of research every week. The actual specifications, the actual numbers, not summaries. Now, what you can actually do about this, because I want to close with something actionable, not just something alarming. Step 1 is the owner's manual. Open it. Find the oil specification section. If your car has a European engineering origin, VW, Audi, BMW, Mercedes, Porsche, Volvo, Land Rover, there will be an ACEA rating or a manufacturer approval number listed. That number is not a suggestion. It is the specification the engine was designed to. It supersedes any API rating. Use an oil that carries that specific approval. The oils exist in America. They are not hard to find. Mobil 1 ESP is formulated to meet several European OEM specs, including ACEA A5B5, and carries certain VW and Mercedes approvals. Castrol Edge Professional line carries specific BMW and VW approvals.
Liqui Moly, the German brand, sells ACEA A3B4 compliant oils at a growing number of American retailers and online. These oils cost more, maybe $8 to $12 more per oil change than a standard API oil. Against the cost of a timing chain or a turbocharger, that conversation is not complicated. The viscosity question. If your European car specifies 5W40 to an ACEA A3B4 standard, do not substitute 0W20 API SP because the label says full synthetic. Full synthetic is a base oil descriptor. It tells you about the oil's origin, not its performance characteristics. The specification is the thing that matters. Full synthetic with the wrong specification is still the wrong oil. On intervals, if you are using an oil that genuinely meets the European extended drain specification for your car, and it carries the OEM approval, not just an ACEA rating that approximates it, you may be able to follow your car's extended service indicator safely. If you're not, if you're running a standard API oil in an engine that was designed for something better, change it more frequently. Shorter intervals partially compensate for lower specification oil, not perfectly, but meaningfully. 12 months or 7,000 to 8,000 miles if you're not running the right spec. The oil brands that actually carry European approvals in American stores, I'm going through exactly which ones to buy next, by name, by specification number for the most common engines this applies to. Because knowing the standard is step 1, knowing which bottle to actually pick up at the auto parts store is step 2. That video is coming. If this is the first time you've heard any of this, and it probably is because this does not get talked about in the spaces where most car owners spend their time, hit the like button. It helps other people who own these cars find this before they have a problem, not after. The owner sitting at 50,000 miles who still has time to change what they're running, that person should see this video. The like button is how they find it. Drop your car and your current oil brand in the comments. I'll tell you if you're running the right specification. Because honestly, the pattern I keep seeing is that people are maintaining their cars diligently and still ending up with early failures, not because they were careless, but because they were never given the right information. Your engine was engineered to survive a long time. Make sure the oil you put in it was engineered for the same thing.